All right, so we are going to start y'all can stop talking about basketball now. Thanks. We're going to go ahead and start the last lecture for the unit, and we're going to be talking about electrolysis or electrolytic cells. So what you need to know about these cells, most importantly, is that our E is going to be what sign if we're non-spontaneous? Minus. So in order to electrolyze something, we actually need a power source of some sort, whether it's something we plug in the wall, whether it's a voltaic cell, a battery. We need something to make this happen. You can read through all of this once I'm done with the lecture. Best way for me is just to go ahead and start talking about electrolyzing things. I'm going to start with the sketch of what's going on when we electrolyze just water, and then I'll go and talk about what half reactions you need to know. So in an electrolytic cell, you only have one container, all right? And in that container, in this particular instance, you can electrolyze any solution, any molten salt, anything like that. But we're just going to electrolyze water, okay? In the electrolytic cell, unlike the voltaic cell, the electrodes are actually just a surface for for reactions to occur on. So we're going to pick some sort of metal that's pretty inert, like tungsten, titanium, platinum, or something. And so I'm going to choose platinum. And again, they're not part of the reaction. They're just hanging out as surfaces. And we're going to attach these electrodes to a power supply of some sort. In this case, I'm just going to attach the electrodes to an actual battery. The sign on the battery translates to the sign of the electrode. So if that's the positive lead, that's going to be the positive electrode. Okay? Now here's the thing that's different from before. The electrode that's positive in the electrolytic cell is the anode. The electrode that's negative is the cathode. So this is opposite to what the voltaic cell did, which makes sense because the voltaic cell is spontaneous. This one's not. Okay, so we have to have that battery to have our supply and our push against this bad potential. Remember EPA van? Electrolytic positive anode, voltaic anode negative. So that'll help you remember that. This is an electrolytic cell, so the anode is positive. But the good news is oxidation still occurs at the anode, and reduction still occurs at the cathode. So what's going to happen is our source of electrons is going to shoot electrons through, and we're going to have electrons running through the circuit. Electrons still go from anode to cathode. That's still the direction of flow, okay? But we're going to get water both being reduced and oxidized because that's all there is in the cell. So water can be both reduced and oxidized, and we're going to talk about the products of that. If you go up the page, let's go back to the previous cell because I want you to be able to write the half reactions for the redox of water. So oxidation and reduction. Whenever you electrolyze something, you're literally splitting it, okay? So we're going to split the water into its elements. So what two gases are we going to make ultimately? Hydrogen and oxygen, correct. So the question is which is which? Which is the oxidation product, which is the reduction product? So the way I remember this, I don't myself have these memorized. I go through this process every time I'm writing down these half reactions, which is no big deal. So oxidation, water is oxidized, so it produces what gas if it's oxidized? Oxygen. So in the oxidation half reaction, water produces oxygen. So therefore, in the reduction half reaction, what gas is produced? Hydrogen. And it makes sense. Look at the oxidation number of the oxygens. It's a -2 in water. What is it here? 0. That's going up in charge. That's oxidation. Hydrogen is a +1 to a 0. That's going down in charge. All right? Now, the next thing you need to realize is one of these is going to be acidic and one is going to be basic. If you remember, every time we did redox balancing, it was either an acidic or basic solution. What do we know about water? It's neutral, right? So we're going to have 1/2 reaction be acidic, 1/2 reaction be basic. The way I remember which is which, oxygen starts with a vowel, acid starts with a vowel. Reduction starts with a consonant, base starts with a consonant. So this one is acidic, this one is basic. So now I just need to balance these just normal, okay? So let's balance the first half reaction. When we balance this, we have 2 oxygens, we need a 2 there. That means we need 4 H pluses, and how do I balance charge? 4 electrons. Okay? So that makes sense. So now, what I like to do here to help the balancing, I'm going to write water just so you can see it as HOH. So I balance this. I have 2 H's and 1 H here. So I'm going to put a 2 there. That gives me 2 OH's. So I need 2 OH's. Do you see what I'm doing? And then, where do I put my 2 electrons? On the left. 2 electrons. So you need to know how to write those half reactions. You could just memorize them if you want, or do what I did and say, okay, oxidation makes oxygen and it's acidic. And then I know my products. And then you can balance from there. Reduction makes hydrogen and it's basic. And I write it out, and then I balance. I don't want you to muck up your half reactions because you need to know these, so just watch what I'm doing here, and then you can write just the overall when I'm done. But if I were to add these up to get the overall of water, what would I add up? What do I have to do first, though? I need to multiply this bottom by 2. So I get a 4, a 4, a 2, and a 4. So if I add these up, don't mess yours up, just watch me, those go away. So what do I have? 6 waters makes 2H2 plus an O2. But what happens to 4 H pluses and 4 OH minuses? It makes 4. Oh, bored. Really? It makes 4 waters. And once I have the 4 waters written down, what happens? They're going to cancel, leaving me with 2. That is the overall reaction for the electrolysis of water. Doesn't that make sense? We're taking water and splitting it into its gases. Okay, so that's important. All right, so now let's translate this back to the picture. So now that I know these half reactions, when I am oxidizing water, what do I make? Oxygen, and it's acidic. So what's happening at the anode, I've got O2 coming off of the anode, and then I've got these H pluses kind of hovering around that electrode, because this is actually all happening near the electrode, near the surface of the electrode. It's not happening over here, it's happening on that surface. So reduction, what's my products of reduction of water? H2 and I don't think OH. Again, y'all are leaving off signs like they're not important. Chem 2 now, I don't want to hear. I think I'm going to start physically assaulting people who forget their minuses. I need to hear charges on things. All right. I think I will. I think push-ups is a good idea. Thanks. Thanks for that idea. It would be a harder slap than a touch, so I think you probably want to do push-ups. Anyway, so I don't need to balance at this point. All I'm trying to see is what my products are. So hydrogen then is the gas that's produced here, and I've got OH minuses all hovering around this electrode. You could actually do this at home. If you got a couple pencil leads and attach them with some sort of wires to a 9-volt battery, and you put those electrodes into water, you'll start to see bubbles coming off both sides, and that's what you're actually producing. And what's really cool, if you take phenolphthalein and put it into that vat, what color does phenolphthalein change and when does it change? Pink when? When? Nope. Right. Acidic or basic is all I'm trying to get out of you. It turns pink in basic solutions. So if you had phenolphthalein in your little experiment, you would start to see a pink fog kind of develop around that cathode because that's where the base is forming. Okay? All right. So are y'all good with that? We're going to now do a bunch of these kind of in a row. I'm only going to draw one more because we can do these without drawing. So we're only going to sketch out the first one. But the main question or the main thing you need to address when you're doing these problems is what products are produced at what electrodes. And that's what the focus is. Most of your questions will be what's produced at the anode in this electrolytic cell, what's produced at the cathode, because that's the whole point of the existence of electrolysis is what we can make. What metals, like sodium solid, for instance, that doesn't exist in nature. Does anyone know why? Incredibly reactive. So it has to be produced and then collected in the production process. It's through electrolysis that we produce sodium solid. Chlorine gas and all the gases you see running around in the big gas cylinders in the back of trucks and stuff, you have oxygen gas, and all that stuff is collected through the process of electrolysis. We're not going to take a sample of air and just pull out the oxygen pieces. We're actually producing it through the electrolysis of water, for instance. Okay? So all we mostly care about in electrolysis is what we can make. Plating jewelry, doing all those kinds of things are usually parts of electrolytic processes. So in the first sketch, and again, I need you to see the difference between what A and B is asking. In A, we're electrolyzing molten sodium chloride, and in B, we're electrolyzing aqueous sodium chloride. What is the difference between those two things? Aqueous is with water. What's molten? It's liquid. It's been melted. You've heard of molten lava, right? It's just the sodium chloride, that lattice has been broken. So what's actually then floating around if the lattice is broken? Na plus and Cl minus, exactly. We have to have free-flowing ions for a current to pass through. A current cannot pass through a lattice. So it has to be very, very high temperature and it has to be molten. So that is a huge difference. So in part A, in our little vat, I'm making the vat really shallow because there's not a lot of room here. All I have floating around are Na plus and Cl minus. That's it. So I'm just going to attach. I'm going to make that the positive side and the negative side of the battery. The positive then is the anode, where oxidation occurs. The negative then is the cathode, where reduction occurs. Now, for the most part, I'm just going to give you a rule of thumb. Metals are the things that are reduced to their solids. Okay? So in this one, the only thing that we can reduce, and again, I'm just going to write a separate note so you don't forget that. Metals are what we reduce. There's very little exception to that. So the metal ion is what we're going to reduce to the metal solid. And reduction occurs at the cathode. So that's going to be reduced. And how do I write the reduction of that in a half reaction? Plus what? One electron makes Na, and that is what's going on. We are taking the sodium ion, and this electrode is being coated with, it's not, since it's platinum, it's not actually part of the process, but it's being coated with sodium solid. All right? That's what's produced at the cathode. So at the anode, obviously the other thing needs to be oxidized. We're not making stuff you don't already know. When we oxidize that, what do you think we make? Cl2, exactly, from -1 to 0. So to balance that, I put 2 there, and then I put 2 electrons on this side. So I'm making chlorine gas at that electrode. So if I were to ask you the question, what are the products of the electrolysis of molten sodium chloride? You would say chlorine gas and sodium solid. That would be the type of stuff you'd be asked. What they use it for is mainly chemistry classes to demonstrate the reactivity of sodium. They don't really, it's too reactive. They don't use it much. But I can buy it and use it for demos, basically. I don't think so. What? They only ship it to high schools with certified chem programs. Okay, aqueous sodium chloride. Now what we're doing, I got to introduce some characters to you. What's different about what's being electrolyzed here? This time we have water and sodium ion and chlorine ions. So I have to introduce you to the world of electrolysis now and talk about electrons. I view electrons running out of that little battery as little chihuahuas running out of a doghouse, going crazy, yipping. You know, chihuahuas are crazy. And they just want to attack things. So there's your chihuahua up there, okay? The chihuahua needs to eat. So it needs to oxidize or reduce something. The chihuahua will, if there's nothing else, like in the first case, there's only two things there. One has to be reduced, one has to be oxidized. The chihuahua is going to do it. But in this case, the chihuahua has options. The chihuahua can reduce not only the Na+, but it could also reduce what? The water. It's going to oxidize the Cl-, but it could also oxidize the water. Which does it do? Okay. This is where I introduce the concept of the bear. The bear is any group 1 or group 2 metal ion. Chihuahuas are so afraid of bears. If water is present, and there's water, hi. If water is present, the chihuahua is going to attack the water before it attacks the bear. I mean, just look at it. You can imagine why. All right? If nothing else is there, though, to reduce, of course it's going to try to attack the bear because it has nothing else to eat. Got it? Now, what about the oxidation portion? If polyatomics are present, they scare, there's Polly. She's a biatch. They hate her. The chihuahuas don't want to be associated with her. So instead of attacking her, they're going to choose to attack the waters. So bears are group 1 and group 2, and then polyatomics are bad. If water's present, water will be reduced or oxidized over those options. Okay? But what if it's another metal like iron 3 or copper 2 or whatever? Well, sure, even if water's present, why not? Why drink water when you could have copper 2? That's exciting. So water is only a choice if a bear is present or a polyatomic is present. Make sense? All right. So now I don't need to draw these. I mean, you get the picture. Do I need to keep drawing this box over and over again? But what I do want to write down is reduction at the cathode, oxidation at the anode. Reduction at the cathode. What are the two options for reduction then in this portion? Na+ and H2O. Which one is the chihuahua going to reduce? The H2O. Why? This is a bear. Now, on the AP, don't say it's a bear. On the AP, you say water, just say water is more apt to be reduced than sodium. What the truth is, most people teach this using the reduction potential table. And you'd go to the table and you'd see that H2O being reduced in those half reactions has a larger number than Na+ does. And so you choose that one over this one. But I prefer bears, and this is more fun. All right, so H2O reduced, what do we make? H2 and it's reduction and it's basic. Okay, so at the cathode, we produce these two things. Now, what are our options at the anode for oxidation? Cl- or H2O. Which one are we going to do? Cl, yeah, well, I have water. That's boring. And what are we going to make? Cl2, and then I have a 2 there. And I know I didn't balance the one above. That's fine. That doesn't change what our products are. And so I make Cl2 gas at the anode and hydrogen gas with OH minus ions at the cathode. Questions? Okay, let's do our next one. We are looking at C, and we're doing aqueous iron 3 sulfate. What's floating around? Aqueous iron 3 sulfate, H2O. Okay, so again, reduction at the cathode. What are my two options? Iron and water. What's the chihuahua going to choose? Iron, and it's going to make iron solid and 3 electrons. So we're making iron produced. This is boring. Oxidation occurs at the anode. And so what are the options there? Water and sulfate. Who's going to be oxidized? Water. Why not this guy? Oh, it's the mean polyatomic. She's crazy. Staying away from her. So what are my products at the anode? Oxidation of water. Oxidation of water. Oxygen and acidic. Good. So iron is produced at the cathode. Oxygen and H plus produced at the anode. All right, and the last one's really easy. Can you look at it and tell me something without even doing anything? It is. I should write it. It's hard to read. Sodium and sulfate. What can you tell me? Yep. Bare polyatomic. Just water. So it's literally going to be oxidation, reduction of water. So we get H2O makes oxygen plus H plus at the anode. And at the cathode, we have H2O makes hydrogen plus OH minus at the cathode. Okay? Sound good? Got it? Got it? Got it? Questions? One thing, did I mention? I don't even remember if I did say the electron flow is still anode to cathode, right? Okay. Make sure you know that. I think I hit it all. So now you've learned 4 more characters today. So let's do now, we're going to bring our physics world and our chemistry world together in these last problems. You guys, this is going to be so easy. You're going to like, this is so crazy easy. What we're using these problems for, these are industrial kind of problems. We already talked about how we make solids. You know, we make sodium solid. We can make gas. If you're in industry producing these things, you want to know how much you're going to make. You want to know how much current you have to pass through your cell. You want to know how long you have to run the cell. And that's what we're basically doing. So in this first example, 13 and 14 are the same electrolytic cell. We are calculating the mass of copper metal produced during the passage of 2.5 amps of current through a solution of copper 2 sulfate. So if we have a solution of copper 2 sulfate, it's a solution. So there's water, there's copper 2, and there is sulfate. That's what's in our electrolytic cell. What are we reducing? Look at the options. We're going to reduce the copper 2 because it's a metal and it's not a bare. And what are we going to oxidize? The water, because the polyatomic is scary. So that's what this first problem is saying. How much copper metal is produced? You just told me copper was being reduced during the passage of 2.50 amps. So we're looking for how many grams of copper. Now, this whole amp thing, amps are not a useful thing in dimensional analysis. What is an amp, really? Yes, a coulomb per second. So whenever you see amp, I want you to immediately change it to coulombs per second. And we're going to run it through, we're going to run the current for 50 minutes. And we want to know how much copper are we going to make. So these are so easy. The best thing to do, though, is you're going to need the half reaction of what's occurring at that cell. So we know now that this is copper 2 being reduced. What is that half reaction? Exactly. So we're producing that, and we want to know how much. So let's start our dimensional analysis. There's only 2 stupid numbers we can start with. So easy. You guys are going to think this is so easy. Let's just start with the 50 minutes. So we need to convert that probably to seconds, right? Well, okay, we're just going to leave it in the dimensional analysis. So I heard it was 3,000 seconds. That's fine. But for every 1 minute, I have 60 seconds. All right. I need to cross over into chemistry world, and I'm going to get there. But there's only one thing I can put in here at this point that's useful, and what would that be? 2.5 coulombs per second. 2.5 coulombs per second. So now I'm stuck. What's something that I can use? There's a number, and we talked about it yesterday. Yes, 96,500. That was the charge in coulombs of what? Coulombs of what? 1 mole of electrons. So for every 1 mole of electrons, I have 96,500 coulombs. Awesome. Now I have moles of electrons. Get me here. Stoic. 2 moles of electrons, we get 1 mole of copper. How do you get me to grams? Now I'm somewhere I'm comfortable. For every 1 mole, I have 63.55 grams of copper. And that's it. How many grams of copper did I make? Someone else get that? 2.47 grams. So as an industrial person, if I need more copper, I could either run it longer or I could increase my amperage. There's lots of things you can do. Okay? So let's look at this next one. This next one is an indication why you need to know these half reactions and need to know how to balance them. Because this says what volume of oxygen gas measured at STP is produced by the oxidation of water that occurs concurrently. Well, we already said that this is a polyatomic, so the thing oxidized had to be the water. So we need to write that half reaction. If we're oxidizing water, what are we making? Oxygen, and it's acidic. So I need a 2 there, a 4 there, and then what? 4 electrons. I need that ratio because I'm looking at liters of this guy. So I'm going to ultimately, in my dimensional analysis, go from there to there. I have to have that 4 electrons in order to do this. Since this is the same cell, everything is going to be the same up to there. All right, so I'm just going to copy it again. 50 minutes. For every 60 seconds, I have 1 minute. And then every second is 2.5 coulombs. For every 96,500 coulombs, I have 1 mole of electrons. Now what? 1 mole of O2 for every 4 moles of electrons. Exactly, 1 mole of O2. Why is 22.4 liters acceptable here? Because we're at STP. Let me ask you something. What if we weren't at STP? What if they said 300 K and 2 ATM? Perv nerd, exactly. If we didn't have those, we would stop here. We would take our moles of O2, and then we'd plug it into PV equals nRT using the conditions we were given. Okay? All right, but we are at STP here, so we're going to use 22.4. And what do we get to 3 sig figs, the volume? 0.435. And the unit on that? Liters. Y'all usually just kill these problems. You usually don't have issues with these, at least traditionally. Feeling okay about them? I think they're fun and easy. But I can't end without having a sexy problem. Yeah, and here's our sexy problem of the day. Or the unit, I should say. I Can't end a unit without a sexy problem. An aqueous solution of an unknown salt of chromium is electrolyzed by a current of 3 amps for an hour. The process produces 1.94 grams of chromium metal at the cathode. What is the oxidation state of the chromium? This is awesome. Let's write a half reaction. We know we're producing solid chromium, right? What don't we know? The oxidation state. Since I don't know it, I'm going to call it X. But calling this X does what? What does that tell us about the electrons? Plus X electrons, right? So at the end of the day, we're trying to figure out what X is. Looking at the information they gave us 1.94 grams of chromium, and then they told us we're running at 3 coulombs per second for 3,600 seconds for an hour. This is basically going to be a two-step process, but what do you think, just instinctually, what's something we can find immediately? Moles of what? Moles of chromium. Let's go ahead and do that. Sometimes you guys just have to play with numbers until you figure it out. So 1 mole of chromium is 51.996 grams. So how many moles of chromium do we have? Okay. What can we find from this? There's something really important we can find from that. What? Coulombs. No. We got the time. Coulombs is known. Say it louder. Moles of electrons. Can't you find moles of electrons from that? Well, let's do it. So we're going to start with 3,600 seconds. For every 3 coulombs, we have a second. How do I get to moles of electrons? 96,500 coulombs for every 1 mole of electrons. So how many moles of electrons do I have? .112. Good. So this is moles of CR. This is moles of electrons. So now, this is the trick to this, and I'm hoping someone sees it. Do y'all see a ratio? It's 4. Where'd you get that? Not 4. It's not 4. It's 0.112 divided by 0.037 is 3. That's the answer. But where do we get that? Look at this. Isn't that a 1? X to 1 is equal to, this is moles of electrons, right? 0.112 moles of chromium, 0.03. That's where it came from. Do you see it? That's sexy. And so you get an oxidation state of a 3, and you're going to get close to a whole number when you're doing these problems. So the trick is realizing it's that. And it's always going to be to 1 mole of the solid, because that's how we write our half reactions. You are officially done with your last official units in chemistry, AP Chemistry. We have 2 more days of just simple organic nomenclature to cover some things that might show up and get you all somewhat prepared for next year, those of you taking organic with me next year. But this is our official last lecture of a unit.